Hey, it's Mr. Shrum, and welcome back to the Periodic Trends tutorial. We looked at atomic radii last time, and now we're going to look at ionic radii, or ionic radius for singular uses. An ion is a charged atom that results from a gain or a loss of electrons. Atoms tend to form ions to achieve 8 electrons in their valence shells. So they're trying to fill up the most outer shell so they can be stable and peaceful atoms. That's all everyone's trying to do. For example, sodium, like all group 1A elements, has a single electron in its outer shell. During a chemical reaction, it loses this electron to form a stable electronic configuration, like that of the noble gas neon, with a +1 charge. On the other hand, a group 7A element, such as fluorine, gains 1 electron to end up with the electronic configuration of neon with a -1 charge. When sodium and fluorine come in contact, a spontaneous reaction occurs, and an electron is transferred from sodium to fluorine. Elements within a group tend to form ions with the same charge. They have similar valence electron configurations and tend to gain or lose the same number of electrons to become stable. Ions in group 1A have a single positive charge, and those in group 2A have a +2 charge. On the other hand, elements in group 6A, like oxygen, form ions with a -2 charge. Elements in group 7A, such as chlorine, form ions with a single negative charge. The noble gases in group 8A are stable because their valence electron shells already have 8 electrons. So they don't tend to form ions. They're not losing or gaining anything. They stay the same, chargeless. The ionic radius is used to measure the size of an ion, and ionic radius is calculated as half the distance between the nuclei of 2 ions. So much like atomic radii is the distance between 2 atoms, between the nucleus of one atom and the nucleus of another diatomic compound. Here, let me go back to the, so the same way they have 2 nuclei of a diatomic molecule and then divides the distance by 2. They do that, but this time it's between ions. And when an atom loses an electron, it becomes a positively charged ion called a cation. When an atom gains an electron, it changes to a negatively charged ion called an anion. Although atoms gain or lose electrons when they become ions, they retain all of their protons and neutrons. And when an atom loses an electron, it becomes a cation. The overall negative charge of the atom is reduced. The remaining electrons are pulled closer to the positively charged nucleus, so the cation has a smaller radius compared to the atom. So these lose electrons, and the remaining electrons are pulled in closer to the positive nucleus. When an atom gains electrons and becomes an anion, the ionic radius becomes larger than the atomic radius. That's because the increase in the number of electrons without an increase in protons. This allows the negatively charged electrons to move farther from the nucleus. So they are getting larger. Anions are getting larger, cations get smaller, right? And a way to remember the cations versus anions, I'll try to annotate it. So cat, think of a cat. Oh my goodness. Those are cat ears, okay? This is really hard, actually. But think of cats as positive. Yeah, positive cats. And anions, think of that as my teachers said it kind of sounds like onion. It looks kind of like an onion, and onions make you cry. So don't cut onions and don't expect to cry. This person is crying, if you can't tell, because he is trying to cut an onion. But remember, cations, cats are cute, positive. Anions sound like onions, which make you cry. That's the best I got. Moving on. Oh God, I should probably excuse me. There we go. Clear all drawings. Okay. All right, now we have a visual aid. If you were to look at periodic trends in the ionic radius, you notice that as you move down a group, the ionic radii of elements tend to increase. Each element within a group gains a new energy level occupied with electrons. This gain increases the overall size of the ion. As you move from left to right along a period, the ionic radii of elements tend to decrease. In the periodic table, the ionic radii of cations gradually decrease from group 1A. But somewhere between 4A and 7A, elements begin to form anions. So these primarily lose electrons to become more stable until about here, they start to gain electrons to become more stable because they have more electrons in their valence shell, and it's easier for them to gain 1 or 2 electrons than lose all 6 or 7. At that point, the ionic radius suddenly increases. And although anions are much larger than cations, they also decrease in size as you move from left to right. All right, so next trend, the ionization energy. Ugh. All right, so when electrons gain energy, they move to a higher energy level. If this absorbed energy is high enough, electrons can overcome the pull toward the positively charged nucleus and leave the atom entirely. The energy needed to pull an electron completely away from its nucleus is called ionization energy. And this is always measured for an element in its gaseous state. To get an accurate measurement, atoms must be separated from each other to minimize any interactions between atoms. The unit of measurement of ionization energy is the kilojoule, or K capital J. Since the ionization energy for each atom is so small, it is measured for a large collection of atoms referred to as a mole. A mole is just a way to say how many atoms there are. So instead of saying 6.02 times 10 to the 23 atoms, we say it has 1 mole, which equals 6.02 times 10 to the 23 atoms. It's kind of like saying, instead of saying I have 100 pennies, you can say I have $1, because 100 pennies is equal to $1. Ionization energies then are expressed as kilojoules per mole. So kilojoules divided by a mole. You need successive ionization energies to remove more than one electron from an atom. The energy needed to pull the first electron from an atom is called its first ionization energy. The energy needed to pull away the second electron is its second ionization energy, and so on. Each successive ionization energy for an element is higher than its previous ionization energy. So here we have an activity. And we can look at the trends. And then we can look at the first ionization energy. Okay. So you can hover over an element on the table, record the first ionization energy for the elements in group 1 in the table below. Round to the whole number. So hydrogen, lithium, sodium, potassium. So we're looking at only group 1 right now. So we have 1,312 kilojoules per mole, 520 kilojoules per mole, 495 kilojoules per mole, 418, 403, 375, 392. So the end result of that is this. You can round, of course. What pattern do you observe? Well, it goes down generally. As you move down a group, the first ionization energy generally decreases. You can also do that for period 2. Starts out at 899, 737, 590, 450, 503, 510, or 509, sorry. So what pattern do you see? Oh, sorry. So that's group 2. However, you're looking at the period for the next question. So we're going to look at the horizontal period. Lithium, 520, 900-ish for beryllium, 800, 1086, 1400, 1300, almost 1700, and then 2000. So the pattern as you move from lithium to neon down a period, the first ionization energy generally decreases. What are your conclusions about the trends of the first ionization energy in the periodic table? Tie your conclusion into your understanding of atomic structure. So, as you move down in a group, the size of the atom increases. The electrons are farther away from the nucleus and it's easier to remove them. So the first ionization energy of the elements generally decreases as you move down. As you move from left to right in a period, the size of the atoms generally decrease. Electrons are closer to the nucleus and it's more difficult to remove them. So the first ionization energy increases as you move from left to right. And this page explains what we just said in that last question. As you move down a group, ionization energy decreases. Ionization energy increases as you move across a period. As you move down in the periodic table, the outermost electrons are farther away from the nucleus and have a weaker attraction. An element that has less attraction toward the nucleus is easier to remove. So the ionization energy decreases as you move down in a group. As you move from left to right along a period, the size of the atoms decreases. The electrons are pulled closer to the nucleus, so the electrons are more difficult to remove. So the ionization energy of elements increases as you move from left to right in the periodic table. So down a group, electrons are further away from the nucleus, experiencing a weaker attraction. And that means it's easier just to take it away from it. So it goes down. But as you move from left to right down a period, the electrons are pulled closer to the nucleus, making it harder to take away. So atomic radii decrease, moving from left to right across a period. As a result, the electrons become closer to the nucleus. What effect does this movement have on the ionization energy, the amount of energy required to remove an electron from an atom? So if the atomic radii decreases, the electron is closer to the nucleus, making their attraction stronger, making it harder to remove an electron, meaning the ionization energy increases. And last trend we're going to look at is electronegativity. When atoms combine to form a chemical bond, they often transfer or share electrons. The ability of an atom to attract electrons in such a chemical bond is called electronegativity. Different elements have varying tendencies to attract electrons. It's easier to remove electrons from group 1A, such as sodium, to give it to a noble gas, or give it a noble gas electron configuration. For a group 7A element, such as fluorine, it's easier to add an electron. So if you only have one electron in your outer shell, it's easier to get rid of it. However, if you already have 7 electrons in your outer shell and you need 8, it's easier for you to just gain one more electron. In a covalent bond, atoms with more electrons in their outer shell are more electronegative and attract electrons more strongly. For example, in the compound hydrogen fluoride, the fluorine atom is more electronegative than the hydrogen atom. So the electrons shared in the bond are pulled more closely toward the fluorine atom, making the fluoride end of the molecule more negatively charged than the hydrogen end. So you can see here this arrow is larger, pointing towards the fluorine side rather than the hydrogen. Ooh, wrong way. So now we have the trends again, and we're going to look at electronegativity now. Trends. Electronegativity. Cool. So we're going to look at group 2 this time. And what pattern do you observe as you move from beryllium at the top to strontium at the bottom? So here, beryllium, we have 1.57, 1.3, 1, 0.95, 0.89, 0.9. So as you move from lithium to francium, the electronegativity values of the elements generally decrease, they go down. Look at the electronegativity graphics value for the elements in period 2 from lithium to fluorine. So as you see, these guys do not have electronegativity because they don't attract or repel. Yeah, they don't deal with this. So it's only through lithium to fluorine for this one. So we have 0.98, 1.57, 2, 2.55, 3.04, 3.44, and 3.98. What pattern do you see moving across a period? The electronegativity values of the elements generally increase. So what can you say about the trends and connect these trends to what you understand about atomic structure? As you move down in a group, the size of the atoms increases. The electrons are farther away from the nucleus. The distance reduces the ability of an atom to attract electrons. So electronegativity values decrease as you move down in a group. As you move from left to right in a period, the size of the atoms generally decrease and the number of electrons in the outer shell increases. This increases the ability of the atom to attract electrons. So electronegativity values generally increase as you move from left to right. And this explains what we said in that last question there. Electronegativity increases moving from left to right. Electronegativity decreases, it goes down from lithium to francium. And as you move down within a group, those new energy levels filled with electrons are added to each atom, and these energy levels are more distant from the nucleus. So the nucleus exerts less attraction on the electrons. The ability of an atom to attract electrons is reduced, which in turn reduces electronegativity. This trend causes the electronegativity of elements to decrease when you move down a group in the periodic table. Going from left to right in the periodic table, new electrons are added to the elements in the same energy level. These electrons are pulled toward the nucleus. An atom with more electrons in the outer shell tends to attract electrons in a bond more strongly than an atom with fewer electrons. This trend causes the electronegativity of elements to increase when we move from left to right in a period. The noble gases, however, are an exception. They have a stable electron configuration, and they don't tend to attract electrons. So their negativity, their electronegativity values are not defined. And that brings us to the summary, everybody. We looked at important characteristics and the trends that they follow in the periodic table. As we move from left to right in a period, atomic radii and ionic radii of elements tend to decrease. Note, however, the ionic radii show a sudden size increase at the point where negative ions, which are anions, are being formed rather than positive ions, which are cations. Also, as we move from left to right in a period, ionization energies and electronegativity values tend to increase. As we move down within a group, atomic radii and ionic radii of elements tend to increase while ionization energies and electronegativity values tend to decrease. You can use your knowledge of these trends to predict how an element will behave in a chemical reaction. For example, Knowing the trends in electronegativity, you can determine which elements might react with each other. For example, sodium has a very low electronegativity and fluorine has a very high electronegativity. These two elements react violently together, with an electron being transferred from sodium to fluorine. All right, so congratulations, you made it through another physical science tutorial walkthrough. And if you have any more questions about periodic trends, be sure to message me and email me. I will tutor you or just talk to you about some questions you have. And yeah, that's all for me, folks. From me, folks. However you say it. But until next time, have a great day, have a great week, and I will see you all next time. Bye-bye.